Hi there, and thank you for attending my talk, Dedekind-Hasse covers and the ugly sweater theorem. Before I get started, let me say a bit about who I am. I did my undergraduate degree at Harvey Mudd College in LA County, California, from 99 to 2003. Then I applied to grad schools and I got into three with full funding. And my top two were Rutgers University in New Jersey and UC Santa Barbara. And Rutgers was ranked a lot higher, probably top 25. But when I visited there, they only had 2 out of 9 current students or graduating students had found jobs. And when I went to Santa Barbara, the grad advisor said that in her 5 years there, she had never seen a domestic student not get a job upon graduation. So it was closer on the beach. It felt right. So I went there. And in my first year, I met Simon, who's running this math circle. He was in like all of my graduate classes as an 18-year-old freshman. So I thought I took some hard courses at Harvey Mudd. It's a pretty rigorous curriculum. I took algebraic topology when I was 20 years old. Went to Budapest to study mathematics at the BSM program. But I showed up and there he is as an 18-year-old freshman in my graduate classes. So yeah, I've known him for like 23 years. So I was at Santa Barbara for 4 years till 2007. I spent the summers at Los Alamos National Lab in New Mexico and then Virginia Bioinformatics Institute at Virginia Tech. And then I moved out there in 2007 and stayed for about 15 months. And then I got a job at Clemson in South Carolina, where I've been ever since. And I've had some short-term visiting positions, like at the Institute for Systems Biology and the University of Southern Denmark. Now, I like mathematics, especially math involving algebraic and combinatorial problems, and I like applying that as well. So my research interests include algebraic systems biology, discrete dynamical systems, algebraic combinatorics, algebra. A more recent application is crystallography and material science, and I just really enjoy visual mathematics. I'm writing a book called Visual Algebra. You can learn all about it on my course website or on my website. Just click Visual Algebra, and I post all of my slides, my homework and exams, and YouTube videos on there. If you want to learn abstract algebra, I'm biased, but I really think it's the best way to do that. And I'll say a little bit more and provide some links at the very end. Okay. Um, so, so now for the main part of my talk, I'm going to talk about an algebraic object called a ring. And even if you don't know, I'm not going to define it formally, but you were all familiar with what this concept is. So it's a set that's closed under addition, subtraction, and multiplication. And that just means if you take anything in there, any two things in there, and you add them, subtract, or multiply, you stay in there. And the most common example of a ring is oops, let me make that a little smaller, is the ring of integers, written as Z. I'm going to actually make that even smaller. Or so R equals Z. I think a little smaller than that. All rings in this talk are going to assume to be commutative, which means that AB equals BA. So we always have A plus B equals B plus A, but if A and B are square matrices, then the order that we multiply them might matter. But in this talk, we will always assume that multiplication commutes. Now, in the integers, you can add, subtract, and multiply, but you can't divide because 1 divided by 2, for example, is not an integer. So if you can divide, you get what's called a field. So a field is a commutative ring that's also closed under division, but of course not by 0. So that's what a ring is. And an ideal of a ring is a subring. That's a subset that's also a ring, but it has an extra property. It is closed under non-zero. It's closed under multiplication. And we write that as I, and so what that means is, let me write it down here. If I is in I and little r is in the ring, then I times little r is in I. So not only is I, or I should say subring I, not only is I closed under multiplication with itself, but if you take anything outside of R and multiply by it, you still get you still stay in I. And in the integers, the ideals all have the form, in plain English, they're the multiples of D. So we write that as this here. This notation means that, how do I want to do this? This means that we're taking all multiples of D where R is in the ring itself. I should probably say Z, because we're talking about the integers. So here's just some examples of ideals. So the integers are the multiples of 1. The multiples of 2, that's closed under addition, subtraction, and multiplication. But also, if you multiply a multiple of 2 by anything, like an odd number, you still get a multiple of 2. So the multiples of 3, 6, 4, etc. There's obviously infinitely many of these, but here's just a few of them, and I've arranged them in this lattice. So this line here means that the multiples of 2 contain the multiples of 6, and the multiples of 4, for example. And what's nice about this is when you can read things like divisibility and factorization properties right off the lattice. In particular, if you have two integers, say a and b, over here like 4 and 6, and then you say, okay, what's the smallest ideal that contains both of them? And that's this thing right here, the multiples of 2. 2 is the GCD, the greatest common divisor of 4 and 6. You can also ask, you say, what's the biggest ideal that's contained in these two? And that's what you get by going down. And that is the multiples of 12. And notice that 12 is the least common multiple. This holds in general, not just for 4 and 6, but for general A and B. So for the integers, we can read things like LCMs and GCDs right off of this lattice. And that's not always going to happen, but we'll see cases when that does. And I want you to notice that there's this kind of duality here. Like if A divides B, then that's equivalent to saying the multiples of B are contained in the multiples of A. So here we know that 2 divides 6, and equivalently, the multiples of 2 the multiples of 2 contain the multiples of 6. Okay, so I need a few more definitions. And that is of primes and irreducibles. This is a concept that you first probably saw in middle school at the latest. So first of all, an element in a ring, if it has a multiplicative inverse, it's called a unit. So the units of the integers are just plus or minus 1. Because those are the only, negative 1 times negative 1 is 1. 2, if you want to multiply by something to get 1, you need 1/2, but that is not an integer. In a field, I should say, I forgot to do this before, a field, the most common examples of a field are the rationals, the real numbers, the complex numbers, and ZP. That's the integers mod P, 0, 1, 2, up to P minus 1. And when we say multiplicative inverse, that just means you can think of that like division. But it really means something you multiply back by itself to get 1. So in a field like this, everything has a multiplicative inverse by definition. So everything is a unit, except for, of course, 0. The units of the ring of n by n matrices, by definition, are just the ones that are invertible. Those, a matrix is invertible if A times A inverse is the identity matrix. This is, I guess, I lied, the only non-commutative ring that will appear in this talk are the matrices. Okay, so just think that an element that's invertible is called a unit. Okay, so an element, little r in a ring, we say is irreducible. In plain English, if it doesn't factor into smaller pieces. So formally, we say if r equals a times b, implies that either a or b is a unit. So for example, 5 um, if does not factor into smaller, so if you try to factor five, it's going to be 5 times 1. It could be -5 times -1. You could do it in the other order, but you can't ever break it up into two smaller pieces. And then an element is prime. Now, I should say this concept of being irreducible, this is what you probably learned to be prime when you learned about prime numbers in middle school. When you hear what is a number, what's a prime? I mean, their only factors are 1 and itself. And that's really the same thing. That's really what this irreducible concept captures. Whereas the concept of being prime is still a little bit different. It says if R divides AB, then R is prime means that either R divides A or R divides B. And let's do that. Let's see how that works with 5. So if 5 divides a product of two integers, say A times B, do you agree that either A is either A is a multiple of 5 or B is a multiple of 5? Of course. So either 5 divides A or 5 divides B. In plain English, if the product of A and B is a multiple of 5, then either A or B must be a multiple of 5. But let's look at 6. So 6 divides, let's say, 12, which is 3 times 4. But it is not true that 6 divides 3, and, or I should probably say, or 6 divides 4. So 6 divides the product of 3 and 4, but it doesn't divide any individual one because it's not a product. So at the integers, these are equivalent statements, but in general rings, they're actually subtly different. So facts that you should remember is that in the integer, these are equivalent, but in every ring, I'm not going to prove this, but being prime implies being irreducible. So this is actually a stronger condition than the first one. And I'll show you some examples in this talk of things that are things that are irreducible, but they're not prime. Okay, so the majority of this talk will involve the rings called the quadratic integers. And to introduce those, I first want to talk about quadratic fields. So if M is a square-free integer, that means it does not divide, does not have any multiple prime factors. And also, I should say M is not equal to 0 or 1, then it's this minor detail. You could define it for these, but not really useful. Then we say Q adjoined root M is just the set of all numbers of the form A plus B root M, where A and B are rational. Now let me emphasize that M could be negative. And if M is negative, then we get complex numbers that are not real. So you could think of this as like a two-dimensional version of the rational numbers. It's like a decreed 2 version. And we know that the rational numbers have this subset that are the integers, the counting numbers, that have all these properties with primes and the basis of number theory. And it turns out that every one of these fields has associated ring of integers inside of it as well. It's like the degree 2 analog of the regular integers. Now, how do you define something like that? Like, what's the degree 2? What do I mean by a ring of integers? Turns out that the definition is easiest to state in plain English, that for a square-free integer, the ring of quadratic integers, called Rm, it's the subring of complex numbers that consists of roots of monic quadratic polynomials. So we're looking at polynomials of the form x squared plus bx plus c. And, the roots of this are of the form negative b plus or minus the square root of b squared minus 4c over 2a. And we're looking at things like this, where that thing under the square root is equal to m. So, and if you think about it, the integers are really the roots of the degree 1 monic polynomials. Like what's a monic polynomial of degree 1? That's something of the form x minus n, where n is an integer. So it turns out that, so if m is square free, it's not a multiple of 4. So modulo of 4, it's either 1, 2, or 3. And if m is 2 or 3 mod 4, then these monic polynomials are of the form z adjoined root m. And let me actually tell you what that is. That is, it's just this definition, but you replace q with z. So it's the set, literally, of all a plus b root m, where a and b are integers. Now, if m is 1 mod 4, you get like twice as many roots of monic polynomials. And what I mean by that, I think if I show you a picture soon, you'll get it. But for now, it's the set of all a plus b 1 plus root m over 2, where a and b are integers. And you can clean this up a little bit and get a better form of this, but I'm just going to show you what that looks like with a picture soon. I think this is the easiest way to really get what this set is. And right now, I don't expect anyone to look at this and be like, oh, I see what that looks like. So the key idea that I want you to remember is that these rings are really like, to the corresponding fields, are like what the integers are to Q. And let me mention that why this thing is a field. Obviously, if you take something like this and you add or subtract or multiply, you get something else like that. But these also have multiplicative inverses. If you take a plus b root m, you multiply by a minus b root m, well, then you get something, then you get something else of this form too, because the root m's multiply together to get an integer. And then if you divide by a squared minus b squared m, you can check that you actually get 1. So everything in here has a multiplicative inverse. So except for 0, and that's why this is a field. Okay, so now I want to show you what these things look like, so you don't have to try to figure out what that formula means. And I'll do it with 2 examples. So when m is equivalent to 2 or 3 mod 4, here's an example when m equals -2. This ring is just z adjoined root m. So here, the elements in this ring are the dots, and this rectangular grid has unit length. This here is the unit circle. I have drawn the units in white. So this is 1 and this is -1. These are the only invertible elements in this ring. And again, this has width 1 and it has height root 2, so like 1.41. And notice that if I replace -2 with -6 or -10 or -14, think of how this picture is going to change. It's just going to sort of stretch vertically and get stretchier. These rectangles get taller and skinny. And so this is what happens for I call this the rectangular case. Number theorists don't seem to like that term. But if m is equal to 1 mod 4, so here's an example of that, -7, then you get basically twice as many quadratic integers. So what I've drawn in black here is the same thing I've drawn here. This rectangular grid of integers with width 1 and height, in this case, root 7. That's 2.23 or something like that. And here's the unit circle with the units +1 and -1. But I also get half integers. So all these gray things are of the form a over 2 plus b over 2 root -7 where A and B are odd. So this thing here, one way to write this set is actually of the form A plus, no, let me do A plus B root -7 over 2, where A and B have the same parity. So they're either both even or both odd. And that's not immediately obvious, but it's pretty elementary to check that's what this thing is. And so here's how you should think about it. In the 2 or 3 case, you got this rectangular grid. In the 1 mod 4 case, you have the rectangular grid in black, but you also have these half integer things that makes it like a hexagonal or triangular grid as well. Okay, so let's do some more examples. This is the case when m equals -1. Now in this case, my notation is a little bit different. The elements in this ring are the lattice points. So like, even though I haven't drawn them, all of these things are elements in the ring. There are 4 units. Notice that the units here are ±1 and ±I. And the things in black are the primes. So the black are the primes. And these are, turns out, the same as irreducibles. So remember I said there will be non-prime irreducibles. That will happen, but not in this ring. Now, these are called the Gaussian integers because they were just, I guess they were used a lot by Gauss when he studied quadratic reciprocity in number theory. And notice that there's some nice symmetry here. So everything is symmetric. So the distribution of primes is symmetric about this axis. That's an elementary thing you can check. And it's also symmetric about these lines as well. So that's why I've drawn it like this. Okay, so these are the Gaussian integers. They're very well studied and understood. Here are the Eisenstein integers. This is when m equals -3. And once again, the black dots are the primes. And that's the same thing as being irreducible. So this time there's actually 6 units. This is the only time that there's 6 units. For all of the other, you know what, something I didn't say, I probably should have. Let me go back. These are the pictures when m is negative. And we are only going to consider the case when m is negative in this talk, because when m is positive, then z adjoined root m just lies in the real line. Everything's real. It lies on this entire line, and you lose this geometric interpretation, and it's generally a lot harder to analyze, and they're a lot less understood in the real case than the imaginary case, for reasons that I won't really get into. So yeah, we're only going to consider negative m. These are sometimes called imaginary quadratic rings, whereas if m is positive, they're called real quadratic rings. Okay, so going back here, this is the only one where there's 6 units. It turns out if m is positive, there's infinitely many units, which is kind of irritating to deal with. And once again, prime and irreducible are the same thing. This ring was studied when people were looking at cubic reciprocity. Okay, so let's do now a more interesting example. So this is where it gets fun. When m equals -5, we have something that we don't have in the integers or the Gaussian integers or the Eisenstein integers. We have things that we take for granted, like everything factors uniquely into primes. That fails. So 9, of course, is 3 times 3, but it's also 2 plus root -5 times 2 minus root -5. And 3 is irreducible. You can't break that up any further. And you can't break up 2 plus root -5 any further either. Similarly, 6 is 2 times 3, but it's also 1 plus root -5 times 1 minus root -5. So when unique factorization fails, we get weird things. We get first non-prime irreducibles. So let me show you what I mean by that. So 3, I claim, is, let me go up here. 3 divides 9, right? So 3 divides 9, but 9 is this times that. So 3 divides 2 plus root negative 5 times 2 minus root negative 5. But 3 does not divide either of these factors. 3 does not divide 2, I'm going to say plus or minus root negative 5. So 3 is not prime. So 3 is irreducible, but it is not prime. So that's one weird thing that happens. You also get something that are called non-principal ideals. Now, a principal ideal, let me write down here. Is just one that is generated by a single element. So it's literally the multiples of some A. So of the form RA, where R is anything in the ring. So a non-principal ideal is something generated by 2 elements. So if I have an ideal generated by, say, A and B, by definition, that's what you get by taking A and B and then adding and subtracting and multiplying however you want, and by anything you want outside that. So it's literally the set of all things of the form A times R, let me use X, plus B times Y, where X and Y are things in the ring. So sometimes, so in some rings, whenever you have things generated by 2 things, you can always find like the greatest common divisor, call it D, and say, well, that's actually generated by 1. So in the integers, if you take 4 and 6 and you say, put those together and see what can you get, that's the same thing as just being generated by 2. But in this ring, we actually get ideals that cannot be generated by a single element, like this. So if we mix and match, if we take like this 3 and we take this 2 plus root negative 5, and we put those together, they take all things of the form 3x plus 2 plus root negative 5 y, x and y are in z root negative 5, you don't actually get everything. Well, you definitely contain, this set contains the multiples of 3 and contains the multiples of 2 plus root negative 5. But you don't actually get the entire ring here. You fall short. So this set is not generated by a single element. And that's not obvious, but it's, and what that means is these 2 things don't have a greatest common divisor. So remember in the very beginning, I said the integers, you can read divisibility and factorization right off of the lattice. And you can read off the GCD and the LCM. And that actually, that's going to fail here because you don't have a GCD. And here's a similar example where if you mix and match, you take a 2 and you take a 1 plus root 5. These things generate an ideal. You don't get everything with those, but you get more than just the multiples of 2 and the multiples of 1 plus root negative 5. So when you have the failure of unique factorization, you no longer get principal ideals. And we say that this ring is not a PID. So a principal ideal domain, I'm not going to write it down, but I'll tell you, is any ring where every ideal is principal. Every ideal is just the multiples of something. When that happens, this divisibility and factorization is really nice because you just read it off the lattice. You have GCDs, you have LCMs. But when you have the failure of unique factorization, you get ideals that are generated by more than one element. So these rings are not principal ideal domains. They are not PIDs. Okay, so that's a fun example to sort of whet your appetite of like what can go wrong, and things can actually go much worse, much more wrong than this, but we won't get there. Let's talk about primes. So we've already seen that in this ring, three or in the 3 is not a prime in z adjoined root -5. So let's think in general what can happen if you take a prime number, a prime integer, and you think of it in a larger ring, quadratic integer ring. There's actually 3 possible behaviors. Before I go over these, let me go down here. It looks like there's 5, but there's some subcases here. So let's start with 11. So 11 is a prime number in the integers, and it turns out that it remains prime in this ring as well. And we don't know how to prove that, but just take my word for it that it satisfies that property that if 11 divides AB, then 11 divides A, or 11 divides B. And equivalently, the ideal, the multiples of 11 is what's called a prime ideal. You don't have to know the definition of it. Let me just tell you. A prime ideal, it is, so an ideal is prime. It's basically if A, B is in P, then A is in P, or B is in P. It's the ideal theoretic interpretation of that divisibility condition. But you don't really have to know that. Just know that prime ideal, in this case, is generated by a prime. Okay, so this is an element that is prime. So we say that this prime is inert. It remains prime in this larger ring. Whereas 29 does not remain prime because 29 factors. 29 is actually 3 plus 2 root -5 times 3 minus 2 root -5. So 29 splits. It factors into 2 smaller irreducibles. And actually, the ideal generated by these things, the product of these ideals is that one as well. And let me tell you what that is. So if I and j are ideals, then the product of I and j, you take all multiples of things in I and things in j, and just see what those generate. So if you have an I1 in I and a J1 in J, that element is in the product of these ideals. But so is the product I2 times J2 for any other I2 and J2, and so forth. So this ring has to be closed under sums. So it's of the form, so you get IN, so you get finite sums where IK and JK, no, sorry, IK is in I and JK is in J. So that's what the product of ideas. So the product of these two things is every multiple of this times the multiple of that, and those are the multiples of 29. As you would probably expect, the product of the multiples of 2 and the multiples of 3 are, of course, the multiples of 6. Now, we saw that 3 is not prime in this ring, but for a different reason. 3 doesn't factor the way 29 factors. But what it does do is these two non-principal ideals that contain it, remember these two things here, the product of these ideals is actually that ideal. So even though 3 doesn't factor as a product of elements, the multiples of 3, that ideal factors as a product of 2 larger ideals. So I say larger because the multiples of 6 are a product of the multiples of these 2 larger ideals. So 29 splits because it's reducible. 3 splits, but it's irreducible. This is a non-prime irreducible. So I'm going to say these things are really So this is what it means for a prime to split. That's the second case. So a prime splits if the ideal it generates, all multiples, is the product of two distinct prime ideals. And you don't really have to know what prime ideal is in the definition, but if the ideal factors, P is inert if if the ideal it generates remains prime in that ring. And finally, the last case is P is ramified if it's not the product of distinct prime ideals, but the square of some prime ideal. So here, 5 is not prime because it factors as root negative 5 times root negative 5, well, times negative 1, which is a unit. So 5, just like 29, I don't want to say it splits because this is a multiple root, but we say it ramifies. And 2 we know is not prime because unique factor 2 divides this product, but 2 does not divide either of these terms. So 2 is not prime, but it doesn't factor in anything smaller. But the ideal generated by 2, the multiples of 2, is the square of this non-principal ideal. That's not obvious from just looking at this, but you can check that. So ramified means that it's the square of some prime ideal. So this is the behavior, 3 different behaviors of what happens, and there's a couple of subcases in both of these. And the remark is that in a non-PID, a split prime or ramified prime may or may not factor, but its ideal will always factor. And that's why it's cleaner to really work with. When we talk about divisibility, talk about ideals. Don't talk about elements. Talk about ideals. Analyze ideals. Things are typically cleaner in that language. Okay, so now that we know what happens with different primes, here's that same picture that I did for the Gaussian and Eisenstein integers. As before, the primes are in black. There's not as many of them. But all the other, here's a unit. Here's a unit circle again. And then the units are +1 and -1. But now all of the other colors are irreducibles that are not prime. And I've color-coded them based on whether unique factors by type, without going into too many details. Remember that 9 is 3 times 3, but it's also 2 plus root negative 5 times 2 minus root negative 5. So here, there's 3. There's 2 times root negative 5, and there's 2 plus root negative 5. There's 2 minus root 5. Notice that if you multiply these two complex numbers, the angles will add, so you get a real number, and the lengths multiply. And the length of this is just 3, because you can see it right there. So this times this equals this squared. And so these red circles really capture non-unique factorization. Similarly, this number, this is 4 plus root 5. Let's write that. So 4 plus root 5, root negative 5 times 4 minus root negative 5. What is that? That's 16 plus 5, which is 21. So that's this thing times this thing, but that is also equal to this times this. So that's equal to 1 plus 2 root negative 5 times 1 minus 2 root negative 5. So all the red dots here are non-prime irreducibles because of the failure in unique factorization, whereas the purple ones are non-prime irreducibles, but not for that reason. The ideal, I won't say any more about that. And the blue ones are the ramified primes, and that's it. So basically, what we take from here is when you have failure unique factorization, you have a lot more behavior. You don't just have primes, and irreducibles being the same, you have primes and you have a more colorful flavor of irreducibles. Okay, so let's switch gears a little bit and talk about something you're probably familiar with, which is the division algorithm. You probably saw this in like middle school or high school. And this is just the division with remainder property. If you have two integers, a and b is non-zero, you could just divide b into a and find a quotient and a remainder. So here's what that is. A equals b times q plus r. And the remainder might be zero, but it's less than b in absolute value. And oh, I said note that r and q need not be unique, need not be unique, not, oops, that's not what I tried to do, need not be unique. And for example, let's try to divide 5 into 23. Most of us would probably just get 4 with a remainder of 3. And here's a picture. You go 1, 2, 3, 4, and now you're inside this little region, and you're 3 units short of 23. So we have a quotient of 4 hops get us inside, and then a remainder of 3. But you could also take 5 hops to get inside and get a remainder of -2. So there's 2 ways to do that. But regardless, we say that the integers is a Euclidean domain because this always works. Anytime that you have this division and remainder property, you get that's a Euclidean domain. And it's not too hard to show that every Euclidean domain is a PID. This is a stronger condition than having every ideal being just generated by one element. Every ideal is just the multiples of something. The Gaussian integers is also a Euclidean domain, and here's just an example. So let's try to divide. Let's try to divide b, which is 1 plus 2i, into a, which is 6 plus 3i. So the same thing we did before. So before we were able to take hops that were positive or negative, but now we're allowed to take hops that are positive. So this is b. We'll go negative b, but we can also go I times b and negative I times b because I and negative I are units. So now we want to so these 4 numbers define a grid. It's like a 2-dimensional version of the last one. We can go in any direction like this, and we want to end up in. And so the fact that we need r to be less than b in norm means that wherever we end up has to be inside of this circle of radius. What's the radius of that? Root 5. And there's actually 3 places we can end up. There's 3 of these things that are in that circle. So we can take, 2 steps in the b direction and -1 step in the ib direction. So we can say 2 minus I times b. If we do that, our remainder is 2. So 1, 2. We can take 2 steps in the b direction and then -2 steps in the ib direction. That's ib. And now our remainder is hold on. No, I did 3 steps in this direction and -2 here, and our remainder is -1 minus I. We've overshot, but we have to go this direction, which is -1 minus I. Finally, we can do 2 in this direction, -2 in that direction to get 2 minus 2IB, and now our remainder is I. So you don't need to know. I mean, just it's worth saying that there's multiple ways to do this. And now I want to show you how this fails for this non-PID. So for this ring, let's try to divide b is 2 plus root -5 into a equals 5. And so multiples of b are in this direction. And now we don't have an I anymore, but we have a root -5. So root negative 5b is in this direction. And so what we need to do is we need to take steps in this grid and end up inside this circle, not on the boundary, but strictly inside, because we need that the length of r. So we can try to go here and here, but then our error vector r, the size of r, it's supposed to be less than the size of b, which is the radius of this circle, but in this case, it's equal. So there's no way to end up inside this circle by following these grid lines. So this is not a Euclidean domain. But I don't know about you. This is picture I think is unsatisfying, because what happens when m gets big? Or as m gets or further away from zero, this grid gets stretchier, and this grid gets bigger, but the circle gets bigger as well. So it's not really clear that this is going to fail for more and more negative m. But I want to show you a better way to think about it. So I claim that Rm is Euclidean, assuming m is negative, if and only if the unit balls centered at points is centered at the quadratic integers actually cover the complex plane. So here's the condition of what it means to be a Euclidean domain. Here, n is just the absolute, is the Euclidean norm, the complex norm, I mean. It's actually the square of it, but that doesn't really matter. You can think of it as just the norm if you want. But this condition, if you divide through by b, says that the norm of a over b minus q is less than 1. And here's how to think about this. If we want to divide b into a, we want to say a equals bq plus r. Then we look at where the quotient a over b lands in the complex plane. So that's going to be somewhere in the complex plane. And we say, is there a quadratic integer, q, that is a distance less than a distance 1 from a over b? Well, if a over b, in this, so let's go back here. Here are the actual quadratic integers. If a over b lands right there, if this is a over b, then yes, it's a distance less than 1 from a quadratic integer. But if it lands here, it is not a distance 1 from any of these 4 quadratic integers, because it's outside all of the 4 unit circles. So, in other words, if we put unit circles at every quadratic integer, and then we have leftover space, then the Euclidean algorithm fail. This condition will fail, and that is equivalent to the original condition of the division with the remainder property. Because notice if a equals this, this is the same thing as saying that a minus bq is equal to r. And so the norm of that, we said, has to be less than the norm of b. And here I'm using n instead of absolute value. Okay, so let's do some examples. Let's do the rectangular case. So m equals -2. This is a Euclidean domain. So we put unit, this is not very stretchy vertically, so this unit ball cover, or this unit ball collection covers complex plane. But if m equals -5, we have these little gaps in here. As we've seen, this is not going to be Euclidean domain. Since this is Euclidean, it's a PID. That's, this is a stronger condition. Over here, just because it's non-Euclidean doesn't mean it's not a PID. But in this case, as we've seen, it's not a PID. So let's do some examples from the triangular case. If for m equals -11, you can see plainly that the unit balls cover the complex plane. This is a Euclidean domain and therefore a PID. Unique factorization is going to hold. However, if we have m equals negative 19, this does not cover the complex plane. So this is not a Euclidean domain, but remarkably, as we're going to see, this actually is a PID. And that's one of the main focuses of this talk is there a alternative visual explanation, a way we can tweak this to see why it's a PID just purely from a picture? And that's a novelty. That's the paper that we wrote and we're submitting hopefully to the monthly. So a quick little background. In the 1950s, Hegner was a German engineer and a recreational mathematician, and he actually proved that if m is negative, there's only 9 values of m that give you a PID. So Rm is a PID. These 5 are automatic because we know they're Euclidean domains. But there's 4 of them that are non-Euclidean but still are PIDs. And that was not taken seriously by mathematicians because, well, he wasn't a mathematician, and there's an assumption that he didn't actually prove, that he assumed. And so it wasn't until, I think, 15 years later, actually right after Hegner's death, that Stark came by and proved that condition, the thing he assumed, and therefore implied, the theorem. So this is called the Stark-Hegner theorem. And here's the novelty of this. So this is the condition about being what it means to be Euclidean, the definition, and this is like the geometric unit ball connection. So this here is what it means for the unit ball covers. And now it turns out that there's a weaker condition here for what it means for one of these to be a PID. And so if we're trying to write A as B times Q plus R, and we want R to be less than B in normal, we can't necessarily do this for a PID, but what we can do is we can say, what if we have AP minus BQ? Let's call that R, and that has to be less than norm than B. So we're basically saying if we can find an element in the ideal generated by A and B that has smaller norm than B, then this ideal is generated by R, or maybe a divisor law. So this is known as the Dedekind-Hasse norm. And notice that this is a special case of it when we can do this and take P to be equal to 1. So when P equals 1, we actually have a quotient and remainder. But when P is not equal to 1, it's just a more general thing. But if we do the same trick we did up here, we divide by B and also by P. We didn't have a P up here. We get this condition. And I claim this as a very nice interpretation in terms of not just unit balls, but smaller balls as well. So now, if we have the complex plane and A over B lies somewhere here, it says if we can find not an integer Q, but a dilate, a P-fold dilate of Q, that's a distance 1 over P away from it. So in other words, if we can find a ball of radius 1 over P, oh, I'm sorry, let me do that again. If we can find some Q and a ball of radius, not 1, but 1 over P that contains this, then it's a PID. So that's what we call this the ugly sweater theorem. My colleague Daniel Martin and I have proven is that if M is negative and we can cover C, the complex plane, with open balls centered at dilates of the quadratic integer rings, of radius 1 over pi, where pi is either an inert prime or maybe a product of inert primes or 1, then it's the PID. And I don't expect you to look at this and be like, oh, clearly I see what he's talking about now. But let me give you an example. So here's negative 19. For negative 19, the unit balls do not cover. But if we add in the balls, so these centers, so these things are the half integers. So this is a quadratic integer. This is 1/2 of it. This is a quadratic integer. This thing is 1/2 of it. This is a quadratic integer. This is 1/2 of that. So if we take the half quadratic integers and put balls of radius 1/2 there, we complete our cover. So this is a PID. And for this one, 2 and 3 are a prime in both of these rings. So if we, our unit balls clearly don't cover, but if we use these balls of radius 1/2, that doesn't work. But if we include the balls of radius 1/3, now we have a cover. And so the idea is that this condition, again, this says that A over B lies in some ball of radius P centered at some Q for every A and B. That just means that these things cover a complex plane. And we call these ugly sweaters because these sort of look like the ugly sweater theorem. They look like those ugly sweaters that we wear, that people wear around the holidays. Now here's a non-example. This is not a PID. We should not have such a cover. But look at this. Here we have the unit balls, and here we have the balls of radius 1/2, and then we have balls of radius 1/3. But the problem is 2 and 3 are not prime. So we're not actually allowed to use these things in the cover. And so this picture does not work because we are not allowed to use these, and so we actually don't have a cover. So let me say a little bit about primes, the discriminant. So the discriminant of a quadratic integer ring, you should think about that as like, b squared minus 4ac. A is 1. So you should think of that as the thing that's under the square root. But that's only partially true. It's the thing under the square root. If m is 1 mod 4, otherwise it has to be 4 times that. The discriminant is just like a number that's attached to a quadratic integer ring. That's either the thing under the square root or 4 times that. And it turns out that the behavior of whether an integer prime is still prime in Rm depends on really just the discriminant mod p. So if the discriminant is not a square mod p, then the prime is inert. If it is a square mod p, it's split. And if it's a multiple of p, it's ramified. Now, you don't need to know this in this talk. This is just a little background information. But also the prime 2, you have to handle it separately because it's the only even prime. And this is inert if and only if m is equivalent to 5 mod 8. And if we, not obvious, but it's hopefully believable that if we want a cover like this to actually work, we absolutely need these balls of radius 1/2 to be in there. In other words, we need p to be 2 to be a prime because the balls get smaller really. So I'm only going to even look at things that are m that are 5 mod p from now on. And there's a lemma that we proved, which is if you have a PID, then every prime less than 1/4 of the discriminant must be inert. So all the small, we need those small primes if we want to have any chance of covering the entire plane. And so here are the values of m that are 5 mod 8, less than 200, bigger than negative 200. And here are the primes up to 71. And this line is 1/4 times the discriminant, or everything to the left of this. So 19 is less than 1/4 of 80, negative 83. And here, the discriminant is just equal to the absolute value of m. So what this says is that if any of these are going to be PIDs, it's absolutely necessary that everything to the left of this red line is prime. So these gaps are going to fail immediately. So the only things that have a hope, any hope at all of being inert, are going to be negative 3, because there's nothing on the left of it, negative 11, negative 19, negative 43, negative 57, and negative 163. These things are completely filled up. Every prime less than 1/4 discriminant is inert. Everything else has to fail. And I think it's and it turns out that all these things actually are PIDs. And I love that, like there's no extra leeway. Like nothing here. We don't have an extra prime at all. We have exactly what we need and nothing else. And I think that's kind of remarkable. So here is a picture proof that these two rings are PIDs. So this first one, I'm using P equals 1, 2, 3, and 4. Remember, product of primes are okay. So 4 is not a prime, but it's a product of a prime. And here we're using 1, 2, 3, 4, 5, 6, 7. And when I made this, I was like, okay, this is nice, but let me just use primes. Let me not use these green ones, 4, and let me throw in some. Let's see, let me throw in the other primes, such as 5, 7, 11, 13, 31, 40. When I was surprised, I threw in all these primes and they didn't work. They weren't enough. And same thing happened here. If I don't use 4 and 6 and I just try to use primes and 1, it doesn't seem to work. But I've only checked a few only two-digit primes. So here's what happens if you have only primes. If you only use primes, so I'm not using those green dots, and you can't really tell what's happening here, but there's there's like something weird going on here. It's like an accumulation point. But let me zoom in. You zoom in on here, that's what it looks like. And here, this is what I've drawn those balls of radius 1/4 so you can see them, how big they are. But look at these little gaps. And here's my question. I don't know the answer to this. I haven't used very many primes. If you use more and more and more primes, like 4-digit and 5-digit and 6-digit, do you actually fill everything in? In other words, can you cover this with finitely many prime balls? Prime balls. If not, what about infinitely? What if you use every prime? Infinitely many of them. Do you actually fill up the whole thing? Or is there like a gap set? I don't have any idea to this. Answer this. And if there is a gap set, what is it? Is it a line? Is it like discrete points? Or is there like some sort of little interior in it, little thickness to it? I don't know. But I did the same thing for negative 163. And look what I got. I got the same thing here. This distance is actually 1/4 times root 163. And I get something that's even weirder. This distance here is 1/6 root 163. And here, look, so here I get the same little accumulation point. Looks like looks like that gap's going to shrink, but I actually get here what looks like a thick gap. But I'm only using two-digit primes. I ran out of memory when I tried to code this for more. Because I'm using LaTeX and Tixie. I didn't expect this. I didn't expect to even have to do this. So I want to ask you, what happens if, or can you fill in these gaps with finitely many primes or infinitely many primes? And if not, what's missing? What does that tell us about these rings? And there's all sorts of questions you can ask about number theory from this visual perspective. You can interpret things visually like this, and I don't think it's ever been done. This is a brand new area of research, open. I have no idea what sort of techniques or tools would even be used for this. I'm not a number theorist, but maybe some of you might. So I wanted to throw that out there as a very open-ended thing to look at. And finally, here's some links. So here's my visual algebra website. It's a QR code if you want. You can follow me on Blue Sky and Twitter. I have a couple papers that have come out recently on visual algebra. And I have a paper that we'll submit in pretty soon, and a forthcoming book. And here's a couple of other books on visual algebra as well. So thank you for sticking around for this talk. Don't hesitate to email me if you have any questions. I'd love to chat about this. And again, this is this is an accident. I wanted to prove that my goal was to prove that R negative 19 was a PID visually for my book, and then it sort of went down this rabbit hole and found that there's a way to do it that works for all 4 of them. So I think this is just the tip of the iceberg. There's a lot more to be done, and maybe you'll be the one to do it. So let me know if you have any questions, and don't hesitate to send me an email. And thank you for sticking around this whole time.